Okay, in this video, I want to talk about the idea of Gaussian elimination. And Gaussian elimination is something that's brought up in the context of matrices, but to understand what Gaussian elimination is and what it's about and how it works, you really don't need matrices at all. And in this video, we're just going to work with systems of linear equations. So what we're trying to do is our goal is to find a systematic way to solve any system of linear equations. So if you have a system of linear equations, let's say that you had something like something simple, like 3x plus 2y equals 1, x minus y equals 2. There are lots of different ways you can solve for x and y, right? You could take the second equation and solve for x in terms of y, and then substitute that back into the first equation, and then solve for y, and then plug that in and solve for x. That's for systems with lots of equations and lots of variables, or lots of unknowns. That's going to be time consuming, but it does work. A more efficient way would be to multiply one of the equations by a constant and then add or subtract the equations. So, for instance, what I would do is I would multiply the second equation by 2, say, and get 2x minus 2y equals 4. And if I combine that with the first equation, so here's my original system. Here's what I get if I multiply the second equation by 2. Now, if I add the two equations, then I'm going to get 5x equals 5. And then I can solve for x. I divide both sides by 5. And then once I see that x is 1, then I can plug that into either equation. So for instance, the second one would be the easiest. I get 1 minus y is 2. And that tells me that y is -1, right? So the solution is xy is 1, -1. But what we want to do is we want a systematic way of doing it that will work for any system of equations. So what I did here was, to decide that I would multiply the second equation by 2, what I observed was that I have a 2y here and a -y here, and so I knew that if I multiplied the second equation by 2, then I'll get a 2y on the top and a -2y on the bottom, and then I can add them, and then the y's will cancel, right? And that's exactly what happened. But if you have another system of equations, so for instance, let's say I changed the x minus y to x minus 7y, and then this, I don't know, let's say this, instead of x I had 5x, then I would maybe try something else, right? So that wouldn't be systematic. What we want to do is come up with one algorithm that you can use, and it will be the same no matter what system of equations you have. So it's not like, well, if I have a -y, then I'll do one thing. If I have a -7y, I'll do something else. That's not what we want. We want something that will just work no matter what the numbers are. Okay? And that's what we're trying to come up with. And so we're going to have to think about how to do that. And the idea is that we want to somehow simplify the system of equations that we have to get a new system of equations with the same solutions. So the key fact that we'll need, this is the key fact behind how it all works, is that there are certain things you can do with the system of equations that do not change the solution. So there are three, let's just call them operations, that do not change the solutions to a system of linear equations. Okay, why don't I just erase the 7 and the 5 just to indicate that's not what the example was. The example, we were just giving an example of how to solve a system of equations, and then the point I was trying to make with this example is that if you had different constants, this method that I did was sort of ad hoc in that it wasn't systematic. If you had different numbers, different coefficients in front of the unknowns, then we wouldn't have done what we did, right? So that was the point behind the example. And now we're getting into the systematic approach. And the key fact is that there are three operations that don't change the solutions to a system of equations. One of them is to swap two equations. In other words, if I had a system of equations, let's just use the one that we had, 3x plus 2y is 1, x minus y is 2. If I swap the two equations and I make the first equation x minus y equals 2 and then make the second equation 3x plus 2y equals 1, these two are considered different systems of equations. But I mean, it's pretty much obvious that the first system here is going to have the same solutions as the second system there, right? No. Oops. Okay, so that's not really interesting. The second one is slightly more interesting, and it's to replace one equation by I was going to say a scalar multiple of the equation. By the equation that you get by multiplying each of the coefficients by the same constant, the same non-zero constant. So by that equation, let's just phrase it as replace one equation by that equation times a non-zero constant. So what that would mean in this example would be something like to replace it by, let's say we could keep the first equation the same, but then we multiply the second equation by, 5. So then you would get 5x minus 5y equals 10. Now, this second system is not any easier to solve than the first system. But the point I'm trying to make is that multiply equation 2 by 5 the point is that that's not going to change the solution. So if I solved this system of equations, I'm going to get the same x and y as when I solve this system of equations, okay? And that's because if you have a solution to the first equation, then you can multiply. If you know that x minus y is 2, then certainly 5x minus 5y will equal 10. And if 5x minus 5y is equal to 10, then certainly x minus y is equal to 2, right? So therefore, one equation, x minus y equals 2, is true precisely when 5x minus 5y is 10. I'm somehow not changing the x and y. I can't have one equation be true but not the other. Okay, and it was really important that I have a non-zero constant, right? Because if I multiplied the second equation by 0, then I'll just get 0. And then I'll have 3x plus 2y equals 1, x minus y equals 2 on the left, and then just 3x plus 2y equals 1 on the right. Well, certainly those will not have the same they will not have the same solution, right? Because, you know, the left system will have only one solution, but the equation 3x plus 2y equals 1 and 0 equals 0 has an infinite number of solutions. Okay, so that's the second thing. And then the third thing is probably the more interesting one, the most interesting one, which is to replace one equation by that equation plus a scalar multiple of another equation. Oh, I'm already using the matrix language. Okay. If you don't like the word scalar multiple, just change it to a multiple of another equation. Well, instead of deleting it, because scalar is fine, I'll just put it in parentheses. Okay. So for instance, if you have 3x plus 2y is 1 and x minus y equals 2, one thing I can do is I can replace, so let's call this first equation equation like 1 and then equation 2. I can replace equation 2 by equation 2 plus, say, 7 times equation 1. Well, what will that give me? I will keep equation 1 the same, so I'll get equation 1 again, but then I'll have an equation 3, which is x minus y equals 2, and then I add 7 times equation 1. 7 times equation 1 is 21x plus 14y equals 7. And if I add them, I get 22x minus plus 10y equals 9. So I'll get this equation 3, 22x plus 10y equals 9. Well, again, this is not any simpler than the first system. Right? I have this system and that system. But the point I'm trying to make is that if I were to solve the first system, I already did that actually. I got 1, negative 1. That will be exactly what I get when I solve the second system. Oh, it's not though. Oh, wait. Sorry, this should be a 13. There we go. Yes. Okay. But we actually can figure out why this is true even without solving. I mean, one way to check that they have the same solution is to just solve both systems and say, wow, you get the same solution. But conceptually, what's going on is that, so the reason why they have the same solution is that, well, on the one hand, if I have equations 1 and equations 2, those will imply equation 3. In other words, suppose the x and y satisfy equations 1 and equation 2. Since I got equation 3, using equations 1 and 2, equation 3 must also hold. Conversely, if I have equation 3 and equation 1, I can deduce that equation 2 must be true. In other words, suppose that I have a solution to this second system of equations. Okay. All right. Somehow I know that I have an x and y that satisfies both equations. Then I can use those equations to deduce that x minus y must be equal to 2. Essentially by reversing what I did to go from 1 and 2 to get 3. I can use 1 and 3 to get 2. And I'll let you think about what I can do. I think I can do, so in this example, if I take equation 3 and then subtract 7 times equation 2, if I take equation 3 and subtract 7 of equation 1, I get equation 2. Okay, so that's a more conceptual reason for why, if I have an x and y that satisfies one system of equations, it must satisfy the other system of equations. I can't have an x and y that satisfies one system without satisfying the other system. All right, so let's just review the three operations. These three operations were: 1, swap 2 equations. Okay, obviously that's not going to change the solution. Replace one equation by that equation times a non-zero constant. And then the third one is to replace the equation by that equation plus a scalar multiple of another equation. And it turns out that just this fact that these three don't change the system of equations will allow us to come up with a systematic approach to solve any system of equations. We'll be able to take any system of equations and simplify that system enough to get a system that we can solve easily. Just by doing these three operations. And that's what Gaussian elimination is. It's a procedure, it's a very specific procedure that if you have a system of linear equations, you apply the three operations in a very systematic way to get a system that you can solve easily. And so that's maybe something I'll talk about in a different video. But anyway, the idea was, so this video is called The Idea of Gaussian Elimination, not, how to do it. The idea is that you can use these three operations in a systematic way to solve any system of equations, and that's what we were trying to do, right? We were trying to find a systematic way to solve any system of linear equations. And Gaussian elimination, there's like lots of different names for it, is a way to do that. And it will consist of repeatedly applying these three steps, these three operations in a very specific order, in a very algorithmic way. So we'll talk about that in another video. Okay, thanks for watching.